Hello, I'm John Chivacco, the co-chair of the NY-GEO 2023 conference and a board member of the New York Geothermal Energy Organization. I'd like to welcome you to this recording of a live presentation from the conference, a two-day event which was held in Albany, New York on April 26th and 27th of 2023. This year's educational sessions and keynotes represent the latest in ground source heat pump system design, product innovations, and installation practices, along with important policy, regulatory, financing, and incentive updates. This presentation is one of over 40 sessions from the two-day event, all of which were recorded and available at NY-GEO's website, www.ny-geo.org, along with session descriptions and a link to download the slides from each of the sessions presented. NY-GEO is proud to make this content available to our members and other industry stakeholders, and if you are a member, thanks so much for your support and participation. If you find this content valuable and for some odd reason you are not yet a member, consider joining NY-GEO at the appropriate membership level with details available at our website. The live recording from the NY-GEO 2023 conference will start in just a moment. Thanks so much for listening.
So this week we've had a lot of great discussions on ground loop design, and a lot of them have been, closed loop or horizontal or vertical traditional systems. And as engineers, I think we realize that that's not always the most practical option. So what happens when that's not the option? So my name is Schauger. I'm an energy engineer and project manager with Labella Associates. We are a full-service architecture and engineering firm located throughout the East Coast and in Madrid, Spain. And a lot of the work that our energy group does is, revolved around, building efficiency solutions and more recently geothermal and district geothermal designs. And as an engineer, a common phrase is, take what the ground gives you. And sometimes, it's not always practical to have your vertical bore field go down 500 feet and have great thermal conductivity. So you have to take different approaches to make sure you're capturing energy in both a technically effective way and also a cost-effective way. So today on our panel, we've got some of our industry's leading experts on their unique approaches to alternative ways of capturing thermal energy, and specifically we're focusing on utilizing groundwater, and by groundwater I mean I'm referring to aquifers underground as a source of thermal energy. So first we've got Roshan Revankar from Genesis, then we've got Andrew Steiner from Darcy Solutions, and last but not least we have Tim Schultz from Terra, Caloric, and they'll each talk about their unique approaches, and then we'll open it up to the Q&A at the end. So without further ado, here's Roshan. Take it away.
Good afternoon, everyone. It's a fantastic time and place to be. I was just talking to the panelists here. New York does hold the record for having highest number of attendees of any state conference in the country. So, in fact, New York attendee numbers have surpassed the national organization's conference numbers. So that's fantastic. So, thank you all for being here. Erin has asked me to summarize technology in 15 minutes, and I'm just going to try to do my best. For those of us who've been involved in this technology, understand the most two different types of heat exchangers that we are all aware of, closed loop and open loop, right? So we do know closed loop gives you the resilience, it just needs a lot more land area. Open loop gives you the performance, but there are fouling issues and so on and so forth. With this technology that I'm going to present here, we decided to combine both these technologies and take the best of both worlds. Some of you have had the chance to kind of touch and feel CLAD, closed loop advection device. So let's just stick with CLAD for now. And had the chance to look and understand and understand the concept. I'm going to summarize it with the next few slides. What you're seeing here is just a schematic diagram of how CLAD works. So nothing different from a typical closed loop system where you have a building, you have a heat pump, flow center, and then closed loop pipes going into the ground. In this case, the closed loop pipes go into a heat exchanger that sits submerged in a water well. On your right, you see what we call the CLAD unit. It's typically 60, 70, or 80 feet deep. That's about it. You only need to hit aquifer depths. What we are doing is there is a pump at the bottom of this heat exchanger which pushes water and provides the advective heat transfer, which makes CLAD perform better. And then this water is then either discharged into a diffusion well or a surface water lake or a pond or wherever you're allowed to do that. A little more complicated diagram here, so I won't take too much time, but in reality, you don't need one discharge for every supply well. You probably need 3 supply wells for a single discharge well. Everything else stays the same. The building side is still closed loop. So it's a closed loop system. You can have antifreeze in it, and it'll still run just fine. On the open loop side, you are pushing water in the direction of water flow. So that way you're not building up or having any thermal plume buildup around the CLAD unit. Now so people do ask, where does this work? Here are a few maps of the US, and what it shows here is the US aquifers. The first map is kind of an overall map to your top left. The second one is where a lot of our focus has been. It's around the Great Lakes region. It's all glaciated aquifers. So this is where you will find enough water at 50, 60, 70 feet deep. You don't need to go deeper than that in most cases. And then there's other regions in the US where this also works because of different kinds of aquifers at different depths. For CLAD, it really doesn't matter what the depth is. It's just about where you find the right amount of water to make CLAD operate. On the open loop side, most open loop systems need about 2 gallons a minute. But for CLAD to operate, we only need half of that, so just 1 gallon a minute of water, groundwater. And on the closed loop side, you can still stick with the traditional 3 gallons a minute per ton. We have currently 3 sized product offerings, and this is sometimes hard to fathom. We have a 6-ton, we have a 20-ton, and we have a 100-ton unit. I like to repeat that. Yes, we have a 100-ton unit. We need about 120 GPM from one well to produce 100 tons of heating and cooling from a single borehole, or a single water well in this case. We've got 3 different efficiencies where these perform between a certain temperature range. The pump at the bottom does not need to run all the time for the system to operate. It only needs to run when you're outside certain temperature ranges. So that helps with the pumping efficiency. What you are seeing here in the picture is basically the product that's sitting outside. So feel free to stop by and take a look at the product there. We do understand that some of these technologies may look nice and fancy on paper, but it has to be practical and easy to install. So we do have design and sales tools to help us do that. We've got a CLAD sizer tool. It's a little different than your typical thermal conductivity and diffusivity. You talk about hydraulic gradient and hydraulic conductivity. So the tool really lets you decide how big a system do you need and how much space do you have to get that done. And we've got other products that help you build a case for CLAD. Just an example of a qualifying example of what a CLAD unit or a CLAD sizing tool can do. The 2 cylinders that you see there it's how much water can you diffuse back into the well, because that's the most commonly asked question. You're drawing water out of the ground, you're putting it back into the well. Can it go back in there or not? So we have a tool that lets you decide how deep you need to go or how wide a well you need to get this done. We do get asked, just like closed loop systems, you do typical TC tests, so you do a test hole. There are tools that are available to figure out if there is groundwater or not. So without having to punch a hole in the ground, there are devices that you walk around on your site and that lets you and gives you a fair idea of how much water is below you and at what depth. There are also a bunch of data that is available, open source, where you can look at other wells in the region. So that gives you a fair idea of how much water is available to make this work. Of course, for larger projects that are 500 tons and above, we recommend doing a test well. Just an example of a cost, because it all comes down to the dollars, right? You need green to go green. An example of a current project that we are wrapping up. On your left, you see the client wanted a typical closed loop design and costs associated with it, so they got quotes for it. And this is them allowing us to share this information. So it's a 150-ton project. The closed loop needed about 72 boreholes at 400 feet each. The total cost of all of the outside work was about $800,000. And then we were able to do all of that with 10 boreholes in 10 wells, basically, at 60 feet deep. And the total cost was less than almost half here. Here is another project that we are working on. What you can see, the yellow dots on the left-hand side is really basically the number of closed wells that would be needed for a project like this. Think about the amount of time, think about the amount of drillers, drilling work, and then connecting all of these pipes. We are replacing all of that with about 14 wells just around the perimeter of the building. Just to summarize, the building loop can still be a closed loop, which means the use of glycol is possible. You could still have glycol, methanol, any antifreeze that is allowed in your region. It is definitely 10 times more efficient than a closed loop with 90% less area. And the prime reason why this happens is because of the type of heat transfer. It's not the typical conductive heat transfer with the ground, but instead you're using water and water to transfer heat against each other, which is obviously a lot more efficient to do. One of the neat things about CLAD is it assures scalability. Now that you know that the land is available, you can always punch more and drop these in and connect them to your existing geothermal systems, or you scale them up as the building use changes or you add more buildings. You can always scale up how many CLAD units you can add. So think of it as sort of a plug and play device as the building grows. There is no thermal buildup because you are constantly recharging and you're using a constant temperature water to draw and do the heat transfer. There is no thermal buildup at the borehole, so you don't have to deal with balancing loads, which is typically a challenge in closed loop systems. And an interesting application is you don't need to abandon the wells due to leakages. If you stop by our booth, you'll notice there is what we call a pitless adapter that sits on top of this unit. What it lets you do is, in case a pump fails or you need to clean up the heat exchanger, you can pull out the whole assembly out of the ground, unscrew the pump, put in a new pump, and put the ground heat exchanger back into the ground. It's fairly simple and easy to do that. A lot of drillers and well contractors are used to doing this on a daily basis, is installing water well pumps. We've made the process as simple as to install a water well pump. So in our industry, this is probably one of the first ground heat exchangers that can be installed and taken out as well. Think of it from a financing perspective. Now you have an asset that is in the ground that you can take it out and go home if your user doesn't pay for it. So this is something someone told us here at the exhibit hall. So this is kind of a neat and unique opportunity that our industry has not had in the past. Product readiness, the product is ready to be ordered. We have about a 6 to 8 week lead time on all three of our product offerings. I like that. Of course, the materials used for this heat exchanger is stainless steel, if you've seen it outside. The reason we have stainless steel is it allows you to do both active and passive heat transfer. Stainless steel being a lot more conductive material than plastic pipe. You don't need to be running the well pump all the time. You only need to run it when you're outside certain temperature ranges. So that really lets you use the pump as little as possible and thereby increasing your efficiencies. And of course, we've got standardized sizing and design tools to go with the product. that really helps you design and make it easier for you as engineers or installers to pick and choose which size you need and go from there. So I do have a slide for frequently asked questions, but I guess I'll leave that for the end.
Sure.
Okay. All right. Thank you very much.
All right, good afternoon. I'm Andrew Steiner. I am Darcy Solutions Chief Development Officer. And Aaron, thanks very much for arranging this today. We're delighted to be here. Before we get into the technology, I thought I'd provide a couple slides, a little context. I'll go through them pretty quickly so we have a chance to talk about the technology. But these are things that are important to us as an organization, I think important to many of the people in the room and why we're here and focused in this industry. And for those of us that are new to the industry, I joined Darcy about 10 months ago. This focus on emissions and climate change was the draw for me to join the geothermal industry. So we all know that buildings are a big problem from an emissions perspective, and they're a big problem that doesn't have an easy solution. And it's one of the reasons that we at Darcy are super excited about what we're bringing to market to help solve this problem. So if you think about the major sectors that are emitting carbon into the atmosphere, think about transportation, we think about the energy sector, we think about buildings. So the energy sector has a plan, is making progress, and is decreasing their emissions. The transportation sector, with the electrification of vehicles, has a trajectory to get there as well. Buildings don't have an obvious path, and so innovation is critical in this space. 80% of the buildings that are standing today are going to be standing in 2050 when we need to get to net zero. It's a huge retro opportunity and a huge retrofit challenge. And not only do we have these existing buildings, we're going to build just as many as we have today, double the inventory globally between now and 2060. So we have to build new buildings in a much smarter way than we have to date. Total global emissions are represented by 30% from buildings, and in colder states like here in New York and places like where I'm from in Minnesota, it approaches 40%. And again, that number is actually going up, not going down, as other parts of the economy get cleaner. So if we want to solve the emissions challenge and our climate challenge, and as I tell my daughters, try to save our planet, it means that we need to solve for heating and cooling. If you add up the black lines on this graph, ventilation, water, and space heating and space cooling, those HVAC systems represent 60 to 75% of the building energy use that we have today. So if we can solve for HVAC, we can solve something on the order of 2/3 of the challenge associated with emissions from buildings. And we're very pleased that Darcy has a solution that can be part of solving this problem. So on the left here, we've graphed a comparison of a variety of technologies for heating. And the graph represents pounds of carbon emitted per MBH of heating. And we see two colors, gray and black. So the black lines are representing fossil fuels, and the gray lines are representing electrification technologies with Darcy in red. And what we've shown here is that the electrification options, these graphs or these bars will decrease over time as the grid becomes greener and there's fewer emissions off-site from energy generation. The electrification technologies will become greener. Natural gas, propane, the other fossil fuel-based technologies will not become greener. They will remain fixed. So Darcy, and we'll talk about the technology here in the next couple of slides, wins on efficiency, and this allows us and allows our project owners and building owners to achieve several things: fully electrifying their heating, making their cooling more efficient, hitting their corporate goals, their net zero corporate goals, and meeting code, meeting regulations. One of the things, we're from Minnesota, one of the things we're hearing from our designers is that the Darcy system was the reason they were able to hit SB 2030, which is state bonded building code around net zero, we were the reason they were able to hit their targets. In addition, like other geothermal technologies, Darcy's eligible for the ITC, this great benefit that's going to power our industry. And as we collaborate with the utilities, especially the electric utilities, are very enthusiastic about this technology because it represents a way to electrify in an efficient way. So I won't clear the slide on who all these folks are, but this is our team. We spun out of the University of Minnesota about 5 years ago. The technology was innovated in the Department of Geology by 2 PhD level geologists thinking about groundwater and how we could harness it. And there's a couple important points on this slide. First, that everyone who is part of this organization joined the organization or founded the company because of this focus on climate. We are wholly focused on decarbonizing buildings, and we want to make a meaningful impact not only on our planet but on the communities where we live. The second point is that it was founded by a group of geologists, and nearly half of our team has either a master's or PhD degree in geology. We are geology focused, and as we explain the technology, we think that's critical for the success of these projects. So I'll get to the system now. So what we're doing is constructing a water supply well. In our case, the largest diameter well is a 12-inch well. It is a cased, fully grouted, municipal grade well. This asset will last 100 years. And into that purpose-built water supply well, we design the wells, we install a heat exchanger. The heat exchanger is also 12 inches in diameter, slides down the well, and we install that heat exchanger with a submersible pump into a targeted aquifer and into a targeted depth that we know is the most productive in that aquifer. We, using the pump, draw water in across the heat exchanger on the open interface of the heat exchanger and push that water back out into the same aquifer without that water ever leaving the ground. So the water stays within the aquifer unit and does not leave. We don't consume any water to the surface. This is important for pumping energy reasons, for chemistry reasons, and for fouling reasons. On the other side of the heat exchanger, we connect the heat exchanger to the building. And in that side, that closed loop, we use just water. The water may be filtered, the water may be treated depending on the regulatory regime that we're in, but that is just water because regulatory guys don't generally think that kindly to circulating glycol through an aquifer. The other benefit of having just water is there's less pumping energy associated with it, and there is also greater capacity to store and transfer energy. So with this design, we are seeing on the heating side 50 to 70 tons of heat per well, and on the cooling side 120 to 135 tons of cooling. And this system scales. We install these wells in parallel to each other, so any individual well can be shut off, serviced from the surface. So what's this do? This makes GEO a viable option for sites that don't have enough space to fit a geothermal solution today. Our sweet spot is going to be in the urban environment where you can put 1, 2, 3, 4 wells on the side of a parking lot as opposed to not having the option for geothermal at all. So what we say, we love traditional geothermal, we love other technologies, we pair with other technologies really, really well, and we believe this technology will enable the market to grow by a factor of 10 because just far more sites will be applicable for geothermal technology than ever before. And indeed, we see many of our early projects in the urban environment. So we've seen a 95% footprint reduction. We are seeing, another critical point is that we're seeing stable groundwater temperatures. Because there's flow in the aquifer instead of a well field that may migrate from 30 to 95 degrees throughout the seasons, we see, and these temperatures are Minnesota-based, 52 degree, consistent groundwater temperature throughout the season, throughout the summer and the winter, and this allows us to have unbalanced loads. It also allows for heating only or cooling only, think data center applications. We're reducing first cost in some cases versus traditional. Depends on the depths and the geology, and our higher efficiencies are certainly helping accelerate payback. We also believe this is a great opportunity for the entire industry, especially partnering well drillers to grow from just a water supply opportunity into a geothermal opportunity on the well drilling side of the market. I'm getting the 5-minute mark here. It's okay because I got about 2. And then real world system performance. So this is data off of one of our earlier systems. This is a 4-well system, and it is a chilled beam system. So, you know, the discussion over the last 2 days has largely been on the heating side about replacing fossil fuels with electrification options and taking carbon out of the emissions profile. One of the very exciting things about this technology and other groundwater technologies is the temperatures we're able to supply to the building allow for passive cooling of those buildings. So this is a chilled beam system where the loop that connects the aquifer to the building is connected directly, not even through a building site heat exchanger, directly into chilled beam throughout the building, and they've completely removed compressors from cooling. So other than dedicated outside air systems, they have no compressors in the system, and they drop their energy cost and their energy usage by 80% using the system. So this is another reason you get great ROI or opportunity for great ROI with this system, but also, again, the utilities are excited about it because if we could drop all our cooling energy use by 1/3 or 2/3, it'd be outstanding for the eventual electrification of all these buildings. So this system is feeding 64 degrees to the wells. We're returning 60 degrees, and we're getting EERs on average. This is the hottest 30 days of the summer last summer. EERs on average of 77 on this system. Compare that with a traditional water-cooled chiller of 20 or 25% for basically a 3x performance improvement. The other side benefit is all those air handling units that were on their roof, 24 of them we removed, they now have space for a solar system on their roof. So in closing on Darcy, Darcy's integrating end-to-end. We're delivering a system to the end building owner, integrating our geologic expertise, product design with the heat exchanger and other components, that system engineering, how we interface with the building side equipment, construction management. We actually act as a PM for the construction and the installation of these systems, working with the driller and other specialties, and as a commissioning agent for our system as well. And we believe this integrated solution delivers higher performance, delivers longer system longevity, and certainly owner satisfaction. And that's it for me for now. Looking forward to questions. Thanks.
Good afternoon, everybody. Tim Schultz, I'm president of Terra Caloric. We're out of northern Michigan, so good to be out east here. Weather's a little nicer than where we are. We still have some snow on the ground, I think. So, thanks to John Chivacco and Scott Smith and Deserta inviting us sort of last minute here, but we're happy to make the trek through Canada to get here. Well, somehow you saw my whole presentation before I. As mentioned, we're out of Michigan, and here's our. I got to turn around a little bit. Our agenda. I'm going to do a quick background on who we are, the problem that we are focused on trying to solve, and I did it again. Our observations of what was going on in the market, and then our solution, what we refer to as hybrid geothermal. And then finally, I'll share some numbers with you guys on what that looks like. Just again, background, we are 75 years this year, actually, construction company. And you can see some of our projects here. Must be on a timer here. My grandpa in the upper right-hand or left-hand corner there, his father, my great-grandfather, started putting in wood furnaces back in the 40s in northern Michigan. And so we kind of have a long history here of not just construction, but working in the heating and cooling space. My father is here in the fourth row, worked with his father there to build, as you see, a lot of commercial and residential properties around northern Michigan. We built our local ice arena. By the way, we came in, I think, fourth last year in the state in our high school, so hockey's a big deal for us. Until we go to Canada, then we usually get beat up. But so a lot of history of building and a focus on energy conservation as we've been building properties. This is our first effort with geothermal. So the upper black and white picture is an old paper mill that is on the Thunder Bay River, which feeds out into Lake Huron. And it was purchased, and then NOAA wanted to build a facility there and a shipwreck museum and wanted to go geothermal. So someone recognized, maybe it was you, Dad, or someone on the project, that there's an old well that hadn't been used in many, many years, and decided to go ahead and tap into that. So right now it's been running for, 18 years, a 44-ton system with 8 rooftop water furnace units that are employed, and was our first LEED certified project that was accomplished. So that was our foray into geothermal. And from that point, we live in northern Michigan. It's a rural area, and we saw a big opportunity to, sorry, I'm not sure why this is on auto change here, to address an issue. So many people are struggling with propane costs, fuel oil costs. Most people, or many people in our area, about 25%, burn wood. Our local college is called the Lumberjacks. So our whole area is known for lumber. And many turn their temperature down and live in a cold, uncomfortable home. And these options are all high emission options they use. So in Michigan alone, rural homeowners are paying an extra $1 billion to heat their home each year. So we kept putting in closed loop systems, and I have closed loop in my home. We have 2 facilities of ours have direct exchange geothermal. We love closed loop systems. We put them in many of our customers. But the typical homeowner near us just could not justify that full cost system. So we said, why don't we just not try to address the entire problem, but address the percentage of it? And when you look at an average home, this is some statistics, some stats from New York and Michigan at 77 million BTU. Most rural homes are not the mansion on the hill, and they still have a problem that needs to be solved. So when you look at those homes, there's something like these pictures here. Modular homes. We're talking about homes that are, in most cases, under 2,000 square feet. You haven't heard that the last two days here. It's been 37-story buildings in New York City, all awesome projects. We're impressed by that. But there's still a lot of people out there that have a problem, and they live in a small home. So when we look at where we live, there are fortunately 1.1 million wells in Michigan alone. These are sort of black dots in each of the what you see here. So there's a high concentration of wells in Michigan. We're certainly surrounded by 6 quadrillion gallons of water, but there's also 1 quadrillion gallons of water in the ground. And so when HVAC companies size, and we did the same thing, when you size a project, you go for the coldest days of the year and the hottest days of the year. So you size the system accordingly. But most of the time, these are some data from Cleveland, it's not that hot and it's not that cold. It's only a handful of days a year. So the majority of systems are way oversized for what it's like most of the time. You build the church for Easter Sunday. The rest of the days, it's way oversized. So what we did was looked at that and applied the Pareto principle. So this green chart here shows a heating season. And again, if you look in the middle of the winter, you get those handful of days or weeks where it's extremely cold, but most of the time it is not. I apologize for this auto change here. In addition, we looked at most dual fuel systems and said, when the heat pump can't keep up, you shut it off, and the furnace, the supplemental heat, turns on and does everything. So what we did, this is our system, we did, instead of an either or, we did an and. And we have a damper over the, if I could change it, I would do it, but I don't know how. Over the furnace we install, and there's a damper over our geothermal heat pump. And that allows both systems to operate simultaneously. And the benefit of that is over the course of the winter, even on the coldest days of the year, you're still getting your full 400% efficiency out of the ground energy, while the furnace just turns on to supplement and get the house to temperature if needed. And that combination of those two things, and because it's an add-on system, we only need 2 gallons a minute for our 1.5 ton and 3.5 gallons a minute for our 2.5 ton total. So it's not 2 gallons per ton, it's 2 gallons total, or 3.5 total. And it's a rare well, at least in Michigan, that cannot handle that. So, 90+% of the wells that we have are candidates now to be a free, clean, renewable energy source for that homeowner, and it's already sitting right there in their yard. So these are the 3 uniques we refer to: a hybrid setup. So again, that simultaneous operation, that's one of our patents, is that we can both run together, where the industry typically does either or. Water efficient, where we've minimized, we're trying to leverage as much energy out of as small a water flow rate as possible to make so many more wells candidates. And then finally, the installation is quite easy. In most cases, it's a one-day project. So again, unlike what you've been listening to, these other examples of big systems, we have some contractors are doing this with one guy in 10 hours, or a couple guys will do it in about 6 to 8 hours, or in and out of the house. And overnight, that homeowner has cut their heating costs by 2/3, and half the homeowners, rural homeowners, don't have air conditioning. They didn't think they needed it, and then they have this, they're like, that's pretty nice, right? So we kind of refer to ourselves as like the plug-in hybrid of geothermal. So here's an important chart. If you look at the bin data, this is actually modeled off of Buffalo, New York, and you look at the total BTUs at each temperature bin throughout the heating season. This is an example of a house that would be, Manual J would say a 50,000 BTU load. We put our 2.5 ton geothermal unit in there, and we're doing over 90% of the heating throughout the winter. So what you see there in the green is our Well Connect geothermal heat pump, and the red is the supplemental propane. So that furnace is still sitting there, and it's there just for those coldest days. In most cases, the homeowner is probably heating or using propane or fuel oil for hot water, for cooking. I know there's been a lot of conversation, I get it, on 100% electrification, but our argument is that we can grow this geothermal to 1%, 2%, 5% of the market or more, but if we can tackle 80 to 90% of the problem for the majority of the rural market, we can make a lot bigger impact than, so it's about more installations than it is the percentage of each installation. Here's a typical install. So to the far right here is an existing furnace. We set our unit right next to it. We tie in the supply and return, thank you, ductwork. It's a 20 amp circuit, so these use about as much electricity as a hairdryer. We add an additional pressure tank because we want the pump cycle to be about a 10-minute cycle when the system is running, 2 minutes on to fill the tanks, 8 minutes resting. So a well pump's going to operate or cycle about 140 times a day on a very cold day, where it's rated to cycle, say, 300 times. So we're working well within the capabilities of the well pump. The water is then discharged out to the ground, much like you'd see a sump pump discharge. And again, with these low flow rates, 5 minutes, getting rid of the water is really quite easy. Every one of our systems has a real-time monitor on it, so I could show you on your phone your system running, you can see it. I would just direct you to the hours. This is a full year, so the system ran 2,000 hours. The furnace ran 12 hours. That's an entire winter. We also show the well pump kilowatt hours that are used to get that water to the surface. And we also show the cooling capacity. So out of all of our systems, on average, we are doing 90% of the heating and all of the cooling. This is just a comparison of fuel oil and air conditioning in New York versus full GEO versus well connect. This just shows our range of performance with our data loggers. So our small units eliminating about 900 gallons of propane, the larger unit a little over 1,000 gallons of propane. But you can see over to the right, these are the home sizes that we're going after. The majority of rural homes fit in that range, even though we're in very small homes and we're in some homes that are even 4,000 square feet, but that's not the target. It's the homes that are not being helped by geothermal systems today that we're targeting. This just shows a couple hundred examples across the x-axis here, and the line shows the BTUs per home. It's sorted from small home to large, and the blue bar is what percent of the total heating our little GEO units are doing. And as you can see, we've got that pretty well filled up there. So again, on average, homes that we're in are about 80 million BTU. We're doing over 90% of the heating. We're eliminating almost 1,000 gallons of propane and saving homeowners, over $1,300 on average. And in most cases, people can 100% finance our system, and that plus their new heating cost is lower than what they're paying today to heat their home. This is a picture of our installations. We're predominantly Michigan, obviously, that's where we live, but we are working our way out to New York. Our contractor on the west side, Zach Mullen, is here today with us. But this is just an example of what we've done. It took us a while to get going, but in the last 5 years, we're putting a few hundred systems in on average and looking to grow that. And this is just a picture of how many households are currently served by wells. And with our hybrid approach, we would argue that there's a high percentage of these that are candidates to be, a free renewable energy source to heat and cool the home. Again, I mentioned my father's here. He won the award. Governor Steiner in Michigan had Innovator of the Year. That was hard to believe 6 years ago now, but time flies. And our system is also approved in Canada. So in summary, we're focused on rural homeowners. Existing homes, retrofit, we have done some new construction, but we're primarily helping people who are already, have a problem and have a home. And we're doing, again, most of the heating. You can see the uniques there. This is our small facility that we make our machines in northern Michigan. And the lower right hand, we put a well in there, and we're heating the entire system with 5 of our Well Connect geothermal heat pumps. And that's it. Okay, cool.
All right, thank you to all of our speakers. I'd like to congratulate everyone in the audience. Only 2 people fell asleep, so it's good.
In that last session, right?
No, I'm kidding. So now we'll open up to questions and answers. Please wait until Matt comes around with the microphone before you speak.
A question for Andrew. Lou Vogel, Tatum Engineering. I wondered, I saw the water in and out of the side of the well, yep. And I wondered what the specifics of how that happens.
Yeah. So you're wondering how the water flows, or how maybe?
How it gets out the side.
Yeah. So we're targeting aquifers that have good porosity, right, for both pulling in as well as pushing back into the aquifer. And so it doesn't work everywhere. Roshan was talking about GPMs earlier. Our largest system requires about 200 GPMs across the heat exchanger. So you need an aquifer that, with that 12-inch diameter, can produce enough space or area to push that amount of water back into the aquifer. Does that make sense? Does that help? Good.
Just following up on that, what's the vertical spacing between the
top and the bottom?
Yeah.
Yeah, typically about 30 feet.
30 feet.
Yeah, so enough aquifer thickness is also required. If
Do you
it's
guys use like
consolidated.
split screens, or do you use just one
It
continuous
depends
like,
on the
wire
yeah.
wrap screen? or
So
something?
if it's a consolidated geology, we're an open bore below the casing, and if it's unconsolidated, we'll split screens. Yeah.
Did you ever look at changing the height of your unit inside the well just to adjust the temperature? Say in summer you can put it up, winter you can put it down, or something like that.
So we really have the gift of the ground here. A lot of the times the ground temperature remains consistent and constant throughout the year, depending on the latitude, on what part of the country you are. So the data that I showed was for 56-degree ground temperature, which remains consistent pretty much throughout the year. So there is no significant advantage to move the heat exchanger, which again would be practically hard to do. Every season you don't want to be fiddling with it. It just needs to stay where it is. And the fact that the temperature really doesn't change much, it's not a great advantage, is our opinion.
I have a question. So for Tim, how deep does your system typically go? Or how far do you need to get to, or you can just go wherever the ground?
Well,
water
they're
is?
existing wells, so whatever they are, they are. You know, we're just looking, as mentioned, it's usually 50 degrees is the average temperature. We're looking at flow rate more than anything. If it's a deeper well, the pressure tank capacity might be sized a little larger because you're trying to minimize that pump cost to get the water to the home. But the depth of the well is not really.
So you won't put a well in then? And you're
We have plenty right now, so we have not. I wouldn't say that people have not installed a well to do this. They have, yeah. Well, actually, we've got two in my folks' house we put in for this. They're in the city and decided not to put natural gas in and put two of our systems in their house. But people have drilled wells to do this, yes. So we're mainly trying to get the cost of geothermal, you know, much reduced, so.
Thanks. As somebody who has had a standing column well for the last quarter century, I guess I would ask, as you're doing this work, how are you integrating domestic water needs in that, and how does operation of the equipment affect water pressure in the house for domestic needs?
Yeah, well, again, our minimum test, well test, so we want to hit 5 gallons a minute so that we're not going to interfere with the domestic needs. And, you know, or we are at least, I mean, we're typically getting 10 plus GPM on standing column. We've done one application on that in Michigan, but again, our wells are pretty deep. We've got a lot of water out here. I'm sure that's going to be that's a more popular option. Household pressure, you know, you're seeing more and more constant pressure systems put in. We frankly don't prefer that with ours because our water flow rate is so low, and that constant pressure pump's going to be running more often than a submersible pump that we want to fill that tank up at the highest efficiency and shut it off. But household pressure is still going to fluctuate between, say, the 40-60 standard. It wouldn't be any different than what they're already experiencing before our system.
Hi, this is for Roshan. Yeah, so you have a well for discharge as well.
Right.
Yeah. How far downstream does it have to be from the input well?
So just a clarification, the discharge well, the way our system is set up is that the water is never pulled out of the ground. It still stays below the ground level, and it is piped into a discharge well, typically 30 to 40 feet away from the production well. There's a lot of applications where you can discharge it into the lake, stormwater, sewer, and to answer the gentleman's question, you could also use it for domestic water or landscaping or whatever use you find for the groundwater. The heat pumps don't like groundwater coming inside the heat pump, else open loop systems are by far the most efficient. But what we are trying to do is exchange the heat and then use the water for other applications. And if there is no use for it, you put it back in the ground without pulling it out of the ground.
Can any of your products be used with wastewater treatment facilities? Thank you. For all of you.
We are not targeting wastewater for our equipment at this point.
No. If you've seen the heat exchangers and same thing with these guys, that will clog things up. But there are other products in the market that are designed to separate the waste and just use the heat. So you should probably be looking at that, for sure. Yeah, but the open loop side is still a heat exchanger, and stuff can get into it, and we probably want to avoid that. So.